which is going to be going over feature engineering and cross-validation. This lab is going to be structured as like a collaborative, so I'm going to be asking for input, and then we're kind of going to be working student solutions for this lab. If you have questions, like you can either answer in the chat box, someone will be watching over that, or like literally just unmuting yourself and just asking, and then we'll do our best to answer your questions. But yeah, why don't we get started? Okay, so today we're just going to be practicing using the, I don't know how to pronounce it, Skitlearn, scikit-learn, to basically do feature engineering and cross-validation. We've been doing a little bit of feature engineering from previous labs, such as like the one-hot encoding. But for this one, we're just gonna be practicing kind of like how do I like train a model, and then how do I test it. So we're gonna import everything like we always do. And then basically we're gonna import this data. So we're gonna be looking at housing prices in Boston. And this is gonna be from the sklearn datasets package. Yeah, feel free to look at other datasets to play with if you wanna explore those in your free time. But we're just gonna load the data, and this is basically just gives us kind of like a key of like what's happening. For instance, like CRIM is just per capita crime rate by town. And as you can see, this is not in the data frame like visualization that we enjoy. And so what we can do is we can just put it into a data frame using pd.dataframe. And now we have everything in like the nice format that we liked. So why don't we get started with question 1. So let's model the housing price down below. And the way we can do it is we can split the data into a training and then a test set. And basically, yeah, why don't we first do that? And it says use the train test split function to split our data so that 10% is used for test. And the reason we basically split the data is because let's say we have like 100 points given to us. If we used our like trained our model on all the 100 points that we had, we wouldn't be able to tell how accurate it was because we don't have any points left to like test whether it can do well with like unknown data, right? And so if we're only given like a small amount of data, what we need to do is set aside some points so that we can be like, hey, I'm gonna test you later. Like first use this portion to like create the model, and then we're gonna use these points that we set aside as our unknown points that we know, and see if the data, like how accurate the model is. Does anybody want to take a stab at this question? I would love for input. Okay, so a lot of people are saying xtrain, xtest equals train test. Okay, yeah. So there's a lot of answers and all of these are correct. So I'm gonna write them here. But basically, you can either do it this way. So you're going to be splitting the x for this one and the y for this one. And the test size is 0.1. So this means that the test points will be 10% of all of our data points that we have. So you can either do it this way, and they all pass, or an alternative, like way to write it, as some other people have mentioned, is that you can just leave it in one line, but it does the same. So you can also just do it this way where you put it into one line, but these two do the exact same thing. Are there any questions about this?
Well, yeah, I have a question. So when you were splitting it using the train test split function, why is it that we're assigning x? Oh, because one is a training group and the other is a test group. So we're assigning two variables to one. Like, do you see what I mean? One function, two variables to one function. Because X train and X test were assigned to the same function. Okay.
So the idea behind this, like, so the reason why we can do the two is because the train test split, like if we have 100 points, you can think of it as kind of a knife, like just like and cutting off like 10% like random 10% of these like data points, and they're going to set them aside into one group, and then the training one will be in another group.
Okay.
And just assigning names. So like the group that we just did was like the train, and then the test is like the little part that we just cut off.
So that function does do that. It cuts it into two.
Yeah.
So you have to assign it to two. Okay. Okay.
Mm-hmm. But like as like let's say we did this one. So instead of this, we did this one. Basically, like you can split it into 4 because you specified I'm going to split X into 2 and I'm going to split Y also into 2.
Okay. Thank you.
Any more questions? Okay. So for question 2, it says that we need to fit the linear model to describe the relationship. And so what they've already done is that they've imported the sklearn linear model. And we're gonna just create like a temporary like linear regression object. But like think of it as like an empty thing. And now what we need to do is we need to fill out this part. So we need to fit it into something so that like it produces, the line that we wanted. Does anyone want to take a stab at this? Well, actually, you don't need to do this one, I don't think, because we're going to be doing it later on. But yeah, does anyone want to take a stab at this one?
Wait, so you don't have to do dot fit in order to do the prediction, or you do need to do dot fit?
Actually, yeah, you do. Sorry. Yeah, you do need to do dot fit. Okay, okay, so 2 people have said different ones. So one is, okay, so 2 people have said that you should do linear model dot fit with X train, Y train. And then one person said that we should do dot fit with X test and Y test. Okay, yeah. So the reason that we're not trying to do it we're not fitting our model on X test and Y test is because we're using those points to like test our model after our model has been like configured and like created. So that's kind of like it's kind of like how in school, after you learn things, you get like a final exam at the end. The test is like our final exam for the model to see how well it's doing. And then the training is like the homeworks, the labs, the discussions, all that kind of stuff. And so for a fit, we're going to be using, as people have mentioned, it's X train and Y train. And so after we fit it, you can think of this as like, in math class, you can think of it as like, okay, now we have this like line that we have on the graph that predicts what we want. And so what should we use for Y pred? Like how should we use our model? Okay, someone asked what linear model dot fit. Linear model dot fit is basically using these data points and we're creating the model. So like when we called linear regression here, it didn't really do anything. You can think of it as like an empty like object right now. But after we do the fit, like we can do it kind of like it like on a graph, it would show like instead of all these scatter points, it would have like a line that cuts through it. So it just like now it can predict something. It created some form of like equation to predict something. If that didn't answer your question, feel free to ask another follow-up question. Okay, so two people have mentioned you could either do linear model dot predict Y train or X test. And yeah, so the reason why we don't do linear model dot predict Y train is because we've technically already trained the model on our training set. So like testing it with something that it already knew is not the best way to test how accurate it is. It's kind of like if I gave you a homework question and then I use that exact same question verbatim on a final exam, I can't really tell if you know the concept. Like I have to give you something that's new. And so yeah, so the way we do it, as other people have mentioned, is that we're going to be using linear model dot predict X test. And what this is doing is it's taking all the like X coordinates from the test part, and it's going to use those, like it's going to plug in all these X values and it's going to give us our predicted Y values. So like if our regression was like Y is equal to 2X and then X test had that like X equals to 1, well then linear model dot predict would be like, okay, 2 times 1, Y predicted is equal to 2. That's kind of what it's doing. It's like plugging in the X values and getting out the Y that we wanted. And so, yeah, after we do that, we can see that we have this like scatter plot thing basically with our Y test and our Y pred. And as you can see, like they're pretty close. Like, if the price was like around like less than 10, the predicted was also kind of less than 10. I mean, we have some outliers, but for the most part, it seems pretty good predictor.
Good question. So why is it that I'm not getting like my axes are a little different. How did you get your axes to be like roughly? It goes from like 10 to 40, like 10 to 50,
Mm-hmm.
and then I'm sorry, 0 to 50, and then 0 to like 40-ish. Mine don't start there. How did you get them there? Because mine don't look, my scatter plot doesn't look linear because it's the axes are not like that. Do you know how?
I technically didn't specify this, but what you can do is you can there's like a function that you can do like X limit and Y limit, like so you can like tell the plot like, okay, stop plotting past this point. I only want X's from.
It's called X limit plot. So
like
plot.
Oh, there's a chat. My scatter plot also looks different.
Yeah.
It seems like some people's scatter plots don't look linear in general. So I don't think that's a plotting formatting issue. I think that might be.
But yours does. Yours is linear.
Yeah, this is what it should look like. So if it doesn't look linear, then
it's not coming out that way for us, is what we're saying, I think.
Are people okay, so oh, okay, so did people do this one or did they do the one line one?
Oh, I did the first one. I didn't do this.
Because okay, so because for the 2 line, if it didn't work, it could be that the X and Y accidentally got separated. So like if I had a point that was like 1 and 2, it treated them as separately and picked random ones so that there was no correlation between the 2. Okay, so for people who did the 2 lines, can you try putting them into 1 line and then running it to see?
Oh, it didn't. Oh.
1 line works?
Wait.
Okay.
Wait. I'm sorry.
Don't do 2 lines because X and Y will be separated, and then like 10% will be randomly picked from each. I don't know if that.
Oh.
Okay. Okay, I think what happened was that when we did it separately, like the coordinates weren't paired together. So like if I picked the first x, the y that was corresponding with it should have been picked. But when we separated, I think it
Okay.
only looked at x, picked a random 10%, and then y, and then picked a random 10%. But those points might not have been like coordinates together. Okay, did that fix things for people? Y was on a different scale. Okay, great. Yay. Okay. So did everyone get question 2? Or can I move on to question 3? How are you able to tell which points are the actual prices and predicted prices on the plot? The labels, like you can just put labels here for it, but basically the x-axis, well, the y-axis was our y-test. No, sorry. So the x-axis we inputted as the y-tests. So those are the like, this is our x-axis, right? Those are the points that like were from our data set. We didn't predict those. And then our y-axis we put as y-pred, but that was from our model that we predicted. So the predicted prices are on the y-axis. Yeah, so each point is a combination of actual and predicted prices. Do outliers represent higher residuals? I'm gonna say yes, because the difference between the predicted and the real price is quite big. Like, can you see my cursor? I don't even know if you can see my cursor. Yeah. But like, do you see like this point? Like the price actually was $50, but we predicted $20. So that's like a $30 difference, which is like pretty big, considering our axis is like from 0 to 50. Why did we use X-test to predict and not X-train? So we used X-test because X-train, like we already fit our model on X-train. Like we already gave it that knowledge. Like as I said earlier, you can think of X-train. Let's think of X-train as like kind of like our homeworks, labs, and discussions. These are the things that we're trying to like build for our model. But like for our end test, we want to give it something that it's never ever like encountered before. And that's what like final exams in school are like, right? Because if I gave you the exact same question as I've given you on like a homework before, I can't really tell if whether you fully mastered the concept or not. And in this way, like the model, like it only like the only way we want a model that can do really well with things it doesn't know, instead of like just things that it knows. So that's why it's X-test and not X-train. And then I guess one last question is, someone asked, how can you tell whether or not the prices and the predicted are big or not? Big is very relative. I think if you kind of just like eyeball it, like as you can see, like for this point, like it's like $30 off, which I think is pretty significant, considering like these points are like like there's basically like a really close like trend. They may be off by like $5 or more. Like 30 is like considered like, it just looks bigger because it's like an outlier. Like, yeah. Okay, why don't we work on question 3 so we're able to finish the rest of the lab on time. But yeah, briefly analyze the scatter plot above. Do you notice any outliers? I think actually kind of discussed this, but yeah, if anyone has any questions about this one, feel free to ask. But I think we discussed most of it. Like you can see there is like a relationship between our price and our predicted price. And I think it's doing a pretty good job. It's just there's only a few outliers. Are there any other questions before I hand it off to John?
I really liked your analogies, by the way, the knife and then all of the other like exam like training and the final exam. You're really good at that. Okay, that was it.
Oh, thanks, guys. Okay. Would the point be approximately 823 to be considered? Where did you get 823? Oh, 23.8. Oh, okay. Yeah, you can I think you can write like a guesstimate of which points you think are outliers. Like this one looks like an outlier, that guy looks like an outlier. But for the other ones, they look like close enough on the trend line to not be an outlier. Okay, I'm gonna pass this off to John so he can do. Wait, actually, just kidding. That wasn't question 3. This is actually question 3. Okay, so question 3 is like, as we find from the scatter plot, our model isn't perfect. And so we need to should we use random state so the graph doesn't change with each iteration? I think that's what the random seed at the beginning did from question 1. This thing. So please don't change this. Otherwise, every time you rerun everything, it's going to give you a new random one and it's going to change. But yeah, keep this guy. Okay, yeah, so we're going to be doing root mean squared error. Fill out the function. And then we're just going to be finding the training error. Does anyone want to take a stab at this? Like for instance, this one, we kind of done it before in previous labs where we're just filling in like what the equation is. Someone said return np dot square root dot mean of actual y minus predicted y squared. Yeah, so we're gonna be doing this one. So yeah, so why are we doing? Yeah, okay. Now we just need to fill out what. Okay, yeah. So actual and then predicted y. So we did square root because this guy square rooted. The reason why we had to include np dot mean between the two is because we have this 1 over n summing it over all the points, and that's the definition of what a mean is. And so we have to do that, and then the y minus y predicted is this part, and we're squaring the difference. Do people want to take a stab also at training error and test error?
Yeah, I can take a stab at this.
Mm-hmm.
So the training error would be the root mean squared error between the y training data and then our prediction on the x training data.
And then, okay. Yeah. Train. Yeah, and then for test error, which variable should we be using for this one?
This would be like y test and then y pred, because y pred is already predicted on the x test data.
Yeah. So we can do this. You could also replace this with y pred. It's the same thing because we specified y pred to be that before. Why don't we?
Mine.
Yeah. Are there any questions about this one?
Mine isn't working. What am I doing wrong? I have an error, but it's probably I probably just screwed up some invalid syntax. What did?
Oh, why don't you private message the chat to me, and
Okay.
so I can let John keep going with the lab, and then we can kind of like work these on.
What is your name? How do I?
Oh, my name's Jessica.
That's
By the way.
So I'll message Jessica. Okay.
Okay.
I just did. Okay.
Why are we doing linear fit again? We don't need. Wait, what do you mean we're not doing linear fit again? We're just doing predicting. You don't have to write this. You can write y pred because we already did it before. It's the same thing. Oh, hold up. Did I write?
Capitalize the y.
Ah, that's why.
Yeah.
I was like, oh my gosh. Yeah, they do the same thing. They're not really refitting it. They're just using it to predict the values. Okay, I'm gonna pass this off to John now for the second half.
Awesome. All right. Hello, everyone. Give me a second here while I share my screen. Share screen. We'll share this. Okay. Let's see. Okay, perfect. And then let me get the chat open. There we go. There's the chat. Okay, perfect. Okay, so we just finished question 3. So now we're moving into the second portion of the lab here, which is on cross-validation. So this is a new lecture concept. I think the lecture just came out yesterday. But essentially, so there's a really great visualization here of what cross-validation is. But basically, in data science, you know, when you're trying to make a model, oftentimes there are a lot of different features that we could want to use in our model. Some might be useful, and some might be completely meaningless and have
We can't hear you.
Can you all hear me now? Is
Yes.
it working now? Okay, yeah, sorry, my internet cut out. Okay, sorry about that. But yeah, basically, so as I was saying, cross-validation is essentially a way in which we can utilize our training data to like determine which features are good. And then once we've determined which features are good, then we can actually use it on the test data set. So that's what this visualization shows. First, we have our total data, then we split it into a training portion and a test portion. So what we did with Jessica in question 1. And then if we still want to, you know, further develop our model, we can do cross-validation to kind of split up our training set into mini tests or training and test sets, and then repeat that process. So one way we could split it would have, you know, this portion be training and this portion be used as kind of a validation. Then we can split it differently and have a different validation set. And we essentially do that so that our validation set kind of passes throughout the entire data set. That's just a quick kind of overview on cross-validation. Now we'll actually work on implementing it. And if anyone has any questions, throw them in the chat. Okay, so question 4. So scikit-learn has built-in cross-validation support, which, you know, later on down the road, you can feel free to use. But for the purposes of this lab, we're going to try and implement it on our own. So we're going to be using kfold.split. So this will actually help split our data sets into these different folds for cross-validation. And then, you know, we'll select the rows and columns that we want to be used for training and test, and then we'll compute the error for each kind of fold that we do. So here's a question. We're defining this this function that'll kind of compute the error for each individual cross-validation fold that we do. So scrolling down, this is what we're going to have to be coding. So first we say that we want to split our data into 4 different folds, and then we'll be storing the errors within an array as we proceed, or I guess in a list. So we have a for loop here. So essentially kf.split is going to give us 4 sets of indices from xtrain that we can then use to split our data. So split xtrain and split xvalid should be using these indices to split our training data into 2 different portions. So with that in mind, does anyone have a guess as to how we can implement code on this side here? So let me get chat open again because it just closed. There we go. Yeah. So again, we're looking for what we can implement on the right here to get split xtrain and split xvalid. Any thoughts? If people are confused, that's fine too. Okay, great. We have some input here. So I'll copy the first kind of line here, and then we can look at it a bit more in depth. So let's look at what's going on here. So first, we are splitting up the training data set. So it's great that, you know, in both entries, we're selecting something from xtrain. So then we're using .iloc. We use .iloc because, again, xtrain is a pandas data frame. We loaded it in back before at the beginning of the lab. And then we're using the train index. So yeah, so train index is going to be a set of indices that'll define the training split that we want to use for this iteration of cross-validation. And then over here, we use the valid index, that's short for validation, because these are the indices of the data that we want to use to validate our cross-validation fold. Perfect. Okay. So then what can we do for splitting our Y train and our Y validation as well? Any thoughts? Oh, actually the first, yeah. Okay, so some people are contributing. I didn't realize the first contribution also had what we would do for Y train. But yeah, we're doing something very similar. Now we're, splitting the Y train. So again, we're using Y train in both cases. The first split, we just want the indices for what we'll be training. And then the second split, we want the indices for what we'll be using as validation. So this code right here, to go back up to the visual, is essentially simulating one sort of split, where valid is this split and train is this split. So that's what we see here. Split X train, split X valid. Okay, perfect. I hear a question?
Yeah, I'm sorry. I keep asking horrible questions.
No, it's totally fine.
So when you're calling .iloc,
Mm-hmm.
and you're calling it on X train and Y train, why, like, you're splitting? What is the purpose of calling it and use it? And what in layman's terms is train IDX and that? Well,
Yeah.
I said this already. I'm just.
No, it's totally fine. I see where the confusion's coming from. So we have to remember what we're doing here. So KF is equal to, this K fold object, and we say we want 4 splits, right?
Right.
So then we take KF and we say, okay, so we've told KF that we want 4 splits. Now we need to feed it something to split. So KF.split is essentially looking at X train and computes 4 equal splits.
Okay.
So it looks at X train, it sees all the indices, and it's like, okay, we found out a way to split this in 4 equal ways.
Okay.
So then it gives you indices to perform those splits, if that makes sense. So it says, okay, we want to, these are the, so train underscore IDX stands for train index. These are the indices that we want to use for the training portion.
Mm-hmm.
And then these are the indices valid under IDX, that stands for validation index. These are the indices that we want to use for the validation portion of the split.
Okay.
So it gives us the indices, and then we need to take the indices and actually select the data that we want. So that's why we do .iloc and then train index and valid index.
Okay.
Does that make sense?
It makes sense.
Okay.
It makes sense. Yes.
Awesome. Okay. So yes, another question.
Real quick. So does the number of splits have to be does the training set have to be divisible by the number of splits?
I don't believe so. I think it might not. I'm actually not sure what it does in the case that, let's say we have like an odd number of data points and then we want to do like 4 splits. I don't know if it just double counts one of the data points or if it just separates it as best as it can. So maybe one split will have 12 points, another one might have 13. If that makes sense. So I'm actually not sure what it does in that case. But you can definitely look in the documentation and, if you read into K-fold, they'll definitely say what they do in that case, but I'm not quite sure. But you don't have to worry about that. It definitely won't error.
Okay, thanks.
Okay. So now we've selected our training and validation data sets. So now we're going to be doing something very similar to what we were doing before. So how do people think we can go about fitting the model in the training split? And again, this function has some model passed in already, so we can reference that in this line. So let me look at the chat for ideas. Where did my chat go? Interesting. Well, my chat's not popping up. That's odd. Any thoughts?
We could do linear model.fit and then pass in the two training data sets. So split X train, comma split Y train.
Yeah, so initially we were using linear model because we defined our model to be called linear model. Here, the function is just taking a general model.
I see.
So instead of linear model, we would do model. But you're exactly right. We would do model.fit. And then we want to fit it onto the training split. And then we also need to give it the response variable for the training split. That's exactly right. Okay. So then for the next portion, so now that we fit the model, we want to compute the root mean square error on these on our predictions. So a reminder, we defined the RMSE function previously. So now the question is, okay, what inputs do we want to feed into our RMSE function? Any thoughts?
Split Y valid, and then our prediction on split X valid.
Yes, exactly. So the first input that we put into our error function will be the actual points. So in this case, that's split Y valid, because these are the points that we've set aside for validation. And then the other input will be our predictions. So we'll do model.predict because we want predictions. And then we want to predict on the validation data. So we feed in split underscore X underscore valid. Exactly. So here we've fit onto the training data. Here we are computing how well our predictions hold up for the validation data. So now we can run that and all the tests pass. Perfect.
Can I ask a question?
Yes, you can.
For the second step where we fit the model, I remember in lecture, they asked us to like make a copy, like clone the model, because they were talking about how as we go through the loop, we need to make sure not to like overwrite it. Why do we not do that here?
Where were we told to do that? Was that in lecture?
Yeah, it was in the lecture video for this. I don't remember which one. It was like one of the Josh Hugg ones. And he kind of like made a point to tell us that we need to clone it. But I wasn't really 100% sure why.
So that's a good question. Interesting. That's not, I don't know. The staff solution on our end definitely doesn't clone the model. Yeah, no, it doesn't seem to have that. In general, it might be the way he was implementing it. I don't know if he was, necessarily defining a similar function that we have in our case. But because we're passing the model into the function, I don't think it should cause any, I don't think it would cause any issues. Because essentially we would generate the model outside of this function, right? And then we would pass the model in as an input. And then it would do all the cross-validation within the scope of the function, and it would leave the model on a global scale unaltered. So I think maybe that's why we're not creating copies here. In
Cool.
general, though, what were we gonna say?
Oh, I was just saying thank you.
Yeah. In general, though, whenever you do model.fit, even if it was fit to something previously, the model will update to be fit on what you just fed in. So within the scope of the function, this won't interfere with previous iterations of the for loop. But yeah, and then again, I don't think we clone because the model on a global scale won't be affected since it's only being changed within the scope of the function itself. Yeah, good question though. Okay, so now we move on to question 5. So we're going to use the function we just made to determine how many of the first n features we should use to get the lowest average validation error. So again, the way this problem's kind of phrased is we've added a bajillion features to this model. I think we have like 52 features. So we're going to be using cross-validation to determine how many of the 52 features are actually features that help our model. And, and then obviously we want to include those and ignore the ones that hurt our model. So that's what we'll be doing here. We'll be implementing the function that we defined. And then we have some hints. We might want to use np.argmin. Awesome. Okay. So let's look at what we have here. So again, we'll be storing the errors for each iteration in a list. So we'll be iterating through the number of features that we have. And then we'll be saying we're trying it, this many features. So here we've initialized our model. It's a linear regression model. And then here's where we're going to be computing the error. So we know we're going to be implementing the function that we just defined. Oh my goodness, CV error to actually perform the cross-validation. So now what are the inputs that we should be putting into our compute CV error function? And just as a reminder, it takes 3 inputs: the model, our training data, and then the response part of our training data. So what do people think we should enter here? And for some reason, my chat still is. Actually, I'm going to try one thing real quick. I'm going to. Oh. Let's see. Can you guys hear me? Okay. I'm going to stop sharing my screen real quick to see. Okay. So the chat's visible now. So hopefully when I reshare, the chat will remain visible. Okay. There we go. The chat is back. Okay. Perfect. Yes. Okay. So I'm seeing some good feedback. Good. Okay. So first input is going to be our model. Of course, we need a model to do cross-validation on. And then the second input we said will be the training data. So first I'm going to fill it out generally, but we're going to have to alter these a little and we'll talk through that. So first thing that we want to do is in this problem, we're using xtrain2 and ytrain2. I think I might have skipped over this code, but these were defined a little bit earlier in the notebook. And the reason why we have a second training set is because we took the first training set, we added a bunch of random extra features, and now we're doing an analysis on all those bonus features. So we have to use the second training set. And then the next portion that we have to use is we have to select the features that we want to examine. So we have to remember, we're iterating through the number of features. So first we're going to start with 1 feature and we're going to go all the way up through 52 features. So on a given iteration of this for loop, we only want to include the first n features. So we're going to be using iloc to make sure that we select, all the rows, but then only the first n columns. And we have to, and then ytrain2 is unaffected. So real quick to explain that again, we only want the first n features of our training data, and then our response variable is one-dimensional, right? Ytrain will always be ytrain, regardless of how many features we're using in xtrain.
Why?
That's why.
Oh, okay. So the reason why the ytrain is one-dimensional is there's only one value in it for every. That's the definition of the function. That's
exactly. Yep. Yeah. By nature of the problem we're working on, our training data, for every row in our training data, there will be one value that it corresponds to in the y variable. Exactly. So yeah. So okay. Colon n. Yeah. The student answer is exactly right. It'll be all columns up to n. So, okay, so we've implemented compute CV error. So now, so this for loop will run and we'll get this errors list, which has the error for each, set of features, right? So we'll have all these errors in an array. So now the question is, how can we easily determine the location of the minimum error in this list? What do people think we do for best num features? Yep. So we have one thought in the chat, use np.argmin. Exactly. So yeah, so np.argmin will determine the location of the minimum value. In this case, we want to know where the error is minimized because we want to use, the number of features that give us the best performance, i.e. the lowest error. That's what np.argmin does. But if we think about it, Python indexing starts at 0. So if the first entry were happened to be the minimum, this would spit out 0. But we know that an index of 0 corresponds with 1 feature, right? So because we want the number of features, we're going to have to offset for the 0 indexing. So we do np.argmin of errors to get the location in the list, and then add 1 to kind of translate that to a number of features. And then, yep. And then this is kind of, yeah, anyway. So then the best error is going to be the error that corresponds with, it is going to be the error that corresponds with the best number of features. So here, that'll just look like the error from our errors array. And then we're kind of offsetting back to what that best error is. So quick question in the chat, what's the difference between argmin and min? Great question. So they both kind of revolve around the same concept. We have a list. Min returns the minimum value in errors. Argmin returns the location of the minimum value. Yes, you could also do min of errors for best error. For some reason, our solution has this. I guess they want you to, incorporate this variable that we just calculated, but min of errors would also work. So an alternate solution would be min of errors. And, that is a bit simpler.
Can I ask a question?
Mm-hmm.
So my issue is that it's when I click run, it's saying reshape your data using the array.reshape -11 if your data has a single feature, or array.reshape 1 -1
Mm-hmm.
in parentheses if it has a single symbol. What?
Yeah. So yeah, so obviously you're not supposed to be getting that error because we just ran and it worked. It seems like you're probably having a shape error, so you might be implementing the iloc incorrectly. Regardless, I can't help debug that, so either try individually messaging Jessica or hopping into office hours once live lab ends, and they'll be able to find your error very quickly. Yeah, okay. But anyway, so we run our code now. So it goes through the for loop. And it prints messages each time it goes through. So we try a total of 52 errors. And then, our code at the bottom determines that the best choice is using 33 features. So 33 features is how many features minimizes the error when we cross-validate. So awesome. So what have we done? So we took this training data that was very overwhelming, had 52 features. We implemented cross-validation and determined that the first 33 features are, the optimal features for our model's performance. Someone in the chat is saying they got 13 features. Yeah, so again, we're using train2 and test2 because we altered the data set. So make sure you implement that on your end and it should fix it. Awesome. Okay. So real quick, we should have time for the last question. There's also this question here. Why is it logical to use a set of features that result in the smallest average RMSE when performing cross-validation? Write your answer in the cell below. For some reason, I think we left the answer in on the student version. So you got a free answer there. But basically, cross-validation is trying to simulate this training-testing relationship. So if something performs well through cross-validation, it's logical to assume that it'll also perform well when we feed our overall test set through it. That's why cross-validation is very helpful for us. We can keep our test set hidden, simulate that, and then run it through our test set at the end. So now that's essentially what we're going to be doing. So finally, fit a linear model using your best feature set and predict housing prices. Okay, cool. So we'll be fitting our linear model. So now I know we're at 2 o'clock. We should finish within the next 2 minutes if you want to stick around. What are people's thoughts for what goes into model.fit here? Again, we want to be fitting our linear model on the optimal set of features for our training data. So what do people think should go into .fit here? Any thoughts in chat? Let's see. It seems like people are confused. Oh, there we go. We have some. Yes, something like that. Exactly. So we'll be doing X train 2 because again, we're using this, thick data set here. And then we want all the rows, and then we want all the way up to the best num features. So you could also just do 33, but we'll use the variable since we defined it. So that's our input data, and then our response variable, again, is ytrain2. So we fit our model. Now we want to compute some errors. So we're actually computing 2 errors here. We're computing training error and test error, which is something I don't think we did in the last portion. So we can talk about why we do that in a second. But real quick, what are the 2 inputs for RMSE if we want to compute training error? So what are some thoughts in chat? Any thoughts? It's a small hint. It'll look very similar to what we did for fitting. Yeah, okay. Thank you, John. Let's see. Okay, so it sounds like it's not working. So so let's try and implement it on my end and see what we can do. So here, the key piece of information is we're trying to compute training RMSE. So we want to input the response variable for our training set. So in this case, that'd be ytrain2. And then we need prediction.
We can't hear you.
Sorry for technical difficulties. Oh, John.
Can you guys hear me now?
Yes.
Yes. Okay. I'm so sorry. Yeah. Okay. So back to what I was.
Well, it's like in and out. We lost you again. So.
You're back. It's okay. You can do it.
Okay. Real quick.
Right now.
Okay. Predictions. So we want to predict. We want predictions on the training set. So we're going to put X train in here instead of X test because we're computing training RMSE. So we want to compare how our model predicts the training data. Then for the test RMSE, we'll do something very similar, but this is the test MSE, so we'll be inputting the test variables. So we'll run this to make sure I didn't goof anything. Oh, I am goofing something. Oh, yes. We want to be predicting. We want to be predicting using the best number of features because that is what we fit on. So if we predict using data that's a different dimension than what we fit on, we're going to get issues. So it's important that the dimensions of our fit data matches the dimensions of our predicting data. So yeah, so now we run it, we get everything that we wanted. We get the training RMSE, we get the k-fold validation RMSE, and we get the test RMSE. So we can see that training has a minimum RMSE, which is expected because we're fitting our model to the training data, we'd expect it to perform well with the training data. If you get really high RMSE on your training data, that's a really bad sign. It means your model probably isn't good for the data and you need to change something. But here we see it's the lowest. Cross-validation, it goes up a little, but it's still pretty consistent. And then test, in this case, happens to be the highest. Sometimes that happens, but the great thing is that they're all relatively on the same order of magnitude. And then we can double check to make sure those values are good. So yeah.
Where did you define best num features?
Best num features was defined within question 5. So if we go back to question 5,
Yeah.
after we did the cross validation, we
Yeah.
set best num features to be the
Oh.
33 features.
And yeah, well, mine didn't work. That's why it's no. Okay.
Yeah.
Okay.
So I can stick around for a few minutes if anyone has any specific questions. Yep, of course, no problem. And then I think there might be some stuff at the end. Yeah, there's a scatter plot here. Oh yeah, I changed it the best model. We can